Alright guys, welcome back. So today we're taking a look at limits and infinity. So this idea is based on as x approaches either positive or negative infinity, or as the value of the limit approaches positive or negative infinity. So first up, when we talk about limits as x approaches positive or negative infinity, we were referring to the idea of a horizontal asymptote of a function, something that we discussed numerous times in both Algebra 2 and Pre-Calculus. So a very useful limit, though, for this material is limit as x approaches either positive or negative infinity of a fraction 1 over x is equal to 0. Now this idea, this limit here applies no matter if the numerator is any number I want it to be, 1 through whatever. As long as it's a number and the denominator is a variable, the overall limit will go to 0. And it makes sense when you think about it. When x is 1, 1 over 1 is 1. When x is 10, 1 over 10 is 0.1. When x is 100, 1 over 100 is 0.01. When x is 1,000, 1 over 1,000 is 0.001. As you can see, as x is getting larger and larger and larger, the decimal is getting smaller and smaller and smaller. It's approaching 0, which is the whole idea behind the limits. So when we're working with rational function limits, as x approaches infinity, and only for x approaches infinity, any of those problems from 1.2 when we were dealing with factoring all the other stuff, we don't do this rule here because it's not x approaches positive or negative infinity. That's very important. As long as it's approaching positive or negative infinity, we are going to divide the numerator and denominator by the highest power of x in the problem. If I see an x cubed in the problem, that's the biggest exponent, everything divides by x cubed, whatever it is. After we do that, any fraction in the form of c over x to the r, c is some constant, r is some power, that fraction goes to 0. And then whatever is left over, the highest power pieces, that's going to be your answer. So we're going to see here, so x approaches negative infinity. We have 3x squared minus 4x plus 1 over negative 5x cubed plus 2x minus 7. The x cubed is my largest power, so I'm going to divide everything by x cubed, which is going to create these fractions right here. The numerator, when I do x squared divided by x cubed, I get an x in the bottom, since 3 over x. X divided by x cubed will give us an x squared, that's why it's 4 over x squared. And there is no variable for the 1, that's why it's 1 over x cubed. And on the bottom, the negative 5 would be left alone because the x cubed would cancel itself. And then 2 over x squared, negative 7 over x cubed. Each of those fraction terms go to 0, so the whole numerator is 0. And then there's only a negative 5 left on the bottom, which means the answer is 0. So this is the idea here. You won't really need to go through this exact process every single time because as long as the biggest exponent is on the bottom, the answer will always be 0. And again, you'll remember this kind of trick from the horizontal asymptotes problems in pre-calculus, where we talked about whenever the big exponent was on the bottom, the horizontal asymptote was 0. And that's what this is right here. It doesn't matter whether x is approaching negative or positive infinity for this problem or for this one, where the exponents are the same top and bottom. So here I divide everything by x to the fourth. I get 3 minus 2 over x squared plus 5 over x to the fourth. Negative 8 plus 4 over x squared minus 7 over x to the fourth. Again, all those fractions go to 0. I'm left with 3 over negative 8. So this was the trick, again, regardless of x approaching positive or negative infinity, where if we were dealing with the same exponent top and bottom, you were going to have the ratio. That was the horizontal asymptote. It was the ratio of the top over bottom leading coefficients. So again, we don't need to go through the division process every single time. We can just go, oh, it's going to be this over that. No problem. The final scenario with our rational functions was the biggest exponent was up top. And you'll notice here when we divide everything by x cubed, we get 5 and then 2 over x squared, 1 over x cubed, 4 over x, negative 3 over x squared, 1 over x cubed. We get 5 divided by 0. That's not good. That's not an actual number. That's undefined. Now, in terms of our limits, we need to specify this as then either positive or negative infinity. Now, where we have to be careful is a lot of students will just simply assume, oh, x is approaching infinity, therefore the value is approaching infinity. And that's not going to necessarily be the case. We kind of need to figure out whether it should be a positive or a negative value that's going on there. So what we're going to do is, it's kind of simple thought experiment. X is approaching a positive infinity. So I'm going to substitute a value like 100 into the problem for x. Now, I'm not going to actually evaluate this in terms of getting a numerical answer here, but I'm going to use this thought experiment to kind of figure out whether or not I should get a positive or negative value when I do this. Now, in the numerator, the x cubed, the 100 cubed, is going to dominate the rest of the problem. No matter what else is happening for the 2 times 100 and the minus 1, 100 cubed is going to be so massive, it's not going to matter. So we focus really only on that. The 100 cubed is going to give me a positive result. Times by 5 is another positive result. On the bottom, the 100 squared is once again going to dominate the rest of the problem. And that's why I'm picking 100. Like, I don't want to necessarily pick a number like, 10 or anything like smaller than that, because it's possible that while cubing and squaring it, if there's a big enough coefficient somewhere else, it might, fight with it and cause a different outcome than I'm looking for. Whereas picking a number like 100, odds are I'm not going to have anything else that's going to be big enough to offset its dominance. So I'm looking at only that 100 squared part, really, and going, okay, 100 squared is positive times 4 is also positive. I'm doing positive divided by positive, I get a positive value. Hence, my answer being positive infinity. Now, if x was approaching a negative infinity, then I would use a negative 100 value to kind of go through this thought experiments. And like I said, don't assume just because it's x approaching infinity, it is infinity like it was in this case. All I got to do is throw a negative in the problem there. Make it negative 5x cubed. Make it negative 4x squared. And I totally change everything. All right, and the same thing with the negative infinity as well. Throwing negatives in there can kind of throw the problem off. So just do a quick thought experiment. Nothing too crazy. You kind of figure out whether it should be a positive or a negative 100 when you do that. Now, this is still a rational function, but it's not really the same kind of ones as before because there's this radical involved. Now, you'll notice that you look at this, okay, the biggest exponent is x squared, which is the numerator, so it's going to be that infinity versus negative infinity concept. But actually, it's not. Because while x squared is the biggest exponent on the top, it is part of a square root, which means it's equivalent to just simply saying x. Well, x is the biggest exponent on the bottom. So this is actually the case of the same exponent top and bottom. And if it's the same exponent top and bottom, then it's the ratio of their leading coefficients. So it would be the square root of 1 over 1, which is just simply 1. Now, like what we just dealt with the whole whether it's going to be positive or negative infinity, any problem with the radical, because technically that radical is plus or minus right now, is either going to be a positive or a negative of that result. And we do the same kind of thought experiments. We substitute the value for x in, going to negative infinity, we're going to use 100, negative 100. And we kind of see what's going to happen here. So negative 100 squared minus 4 times negative 100 plus 3 over negative 100 minus 5. So the numerator, negative 100 squared, is going to dominate the problem. It's going to become a positive value. Square roots of positive is positive, so the numerator stays positive no matter what. Whereas the denominator, negative 100 minus 5, is clearly a negative value, and positive divided by negative is negative. Which means our answer is going to be negative 1. Not the positive one we got from doing the ratios, but negative 1 because here the limit as x approaches negative infinity affects the problem. So again, with our 4 examples, when we were just dealing with our simple rational functions, biggest exponent on the bottom or exponents the same top and bottom, x does not care about whether it's negative or positive infinity, and it just works as either 0 or the ratio of the coefficients. However, when the biggest exponent's up top, or we're dealing with a radical, it does matter, and we have to consider the positive or negative results of the problem. We do a little thought experiment to kind of figure that out. All right, so that's our rational function and then the squared portion there. We also have some stuff involving exponentials and logs. Now, I'm using e to the x and ln of x, so it's all base e. These rules would still apply if it was like 2 to the x, or log base 5 of x. The rules still apply to that. So e to the x, e to the infinity is infinity, e to the negative infinity is 0, and whether it's positive or negative infinity, e to the 1 over x, or a fraction in general, is going to always be 1. Natural log going off to infinity is infinity. Natural log can't go to the negative side because it can't take a negative of natural log, can't take a 0 either. That's why it's saying 0 from the right of ln of x is negative infinity. All right, and that's just in general where the vertical location is. If we were talking about ln of x, let's say like minus 4, it would have to be the limit as x approaches 4 from the right. because that's where the vertical asymptote would be. All right. So if we look at the idea here, what we're going to want to do is we're just going to want to substitute infinity into for x and just kind of see what exponent we get here. So negative e to the negative 3 times infinity minus 3. Negative 3 times infinity is a negative infinity. Negative infinity is going to be 0 for the exponential. So negative 0 minus 3 is just simply negative 3. All right, we do the same kind of thing with any of the e problems. Just kind of fill in the infinity there or the negative infinity. Just kind of do a quick calculation. If there's a number multiplying with it, just the signs. Negative times positive is negative. That's why this became a negative infinity. Just kind of work out whatever that is there. And then for same thing with our natural logs here, we have a negative infinity multiplying with the 2. So ln of negative 2 times negative infinity. Negative times negative is positive, so this will then be 4 ln of positive infinity, which is infinity, and 4 times infinity is, again, still infinity. So keep in mind, if that had been a negative 4 on the outside, then this would be negative infinity, because it would be a negative times a positive infinity result. All right, so they're pretty straightforward, the exponentials and logs. Just be careful with those different rules. Now, the last thing is we had talked about horizontal asymptotes. We also have what's called vertical asymptotes. These are where you are dividing by 0 in your function. And there's two main possibilities that could occur, and that's what the graph is showing us. It's a little bit older from an old textbook, but it's a good visual representation of what's happening. Here we have two different values, limits at a and b. We can see at a and b both have vertical asymptotes. The difference is on a's vertical asymptote, both left and right sides, the value of the function is going up to infinity. Since left and right side are the same value, the limit at a is going to be positive infinity because they converge together. Doesn't matter they don't actually reach a number, they're both the same values, therefore the combined convergence is infinity. Whereas at b, left side's going up to positive infinity, right side's going down to negative infinity, so at b it does not exist because they're not the same number. And that's kind of why you want to be very careful and not say d and e when the answer should be positive or negative infinity, because yeah, kind of technically, infinity doesn't really exist, but we want to say it does not exist more for situations where it literally is not possible, left and right are not the same. Now, more often than not, you're not going to have a graph for that. We will recognize that if I substitute 1 in, I am going to get 1 over 0, so that tells me I have a vertical asymptote. So we need to figure what's happening for the left and right sides. So what we kind of do here to figure out the left side limits for this is we're going to pick a number that's very close to 1 from the left, like 0.9. And go, okay, I get 1 over a negative 0.1, which is a negative value. Hence, I would say the left side limit is negative infinity. It's clearly going down. Again, we have to pick it close. You don't want to necessarily pick an integer value. I mean, this is a simple one, so you could clearly see it would only change at 1. But if the more complicated problem involving more x's up top, more x's on the bottom, you don't want to accidentally pick a value that would be on the opposite side and therefore change everything. So pick something that's super close, just a simple decimal point away, 0.9. Again, it's a thought experiment. We're not actually doing a full calculation. It's more just checking positive versus negative values. Same thing's happening on the right side. So right side of 1, for the 1 over x minus 1, I would use a 1.1. So I see 1 divided by 0.1. I have positive divided by positive. This is positive. Therefore, the right side goes off to positive infinity. So left is going down, right is going up. They are not converging. Therefore, I would say this limit does not exist. It's not approaching the same number. And that's typically going to be the case whenever you have a situation where the vertical asymptote is just an expression, not being raised to a power. Or if it is being raised to a power, it's being raised to an odd power. That will allow you to typically have this going in opposite directions. Whereas if we have a situation like this one, where this actually factors as x plus 4 over x plus 3 squared, we can see the squaring there is not going to change the bottom in the slightest. So it's going to be all about, okay, so the bottom is going to stay positive no matter what. As long as the top stays positive versus top stays negative, it's going to approach the same direction from left and right sides. And we can see that pretty quickly. When we do limit as x approaches negative 3 from the left side, we pick a number like negative 3.1. We get a positive 0.9 over a positive number, which means I'm going off to positive, which means I'm talking about positive infinity here. And then the limit as x approaches negative 3 from the right side, so I'd use like a negative 2.9. Squaring the bottom is still positive no matter what. Top adding with 4 gives me a 1.1. So it's different value, but it's still a positive value, so it's still positive infinity. We can see that this overall limit will converge to positive infinity then. All right, now, again, more often than not, you'll see the vertical asymptotes on a graph. But if you ever do see as part of a algebraic problem, they want limit as x approaches this number, and you get like 2 divided by 0. It's a vertical asymptote, and we got to figure out what's happening before and after to see whether it's going to positive infinity, negative infinity, or if it actually simply does not exist, which for the most part will generally be the answer, because it has to be the expression being squared at the vertical asymptote for it to not change directions there. All right, so that's it for our limits at infinity. Our last topic is going to be discussing the idea of continuity, and I'll see everyone next time for that.